Okay, thank you very much. So it's an honor to give another talk at this great seminar. So I'm going to talk about Lorentzian scattering rigidity, and in particular about the rigidity of stationary metrics. And the date here is wrong because it's the last time I updated the file. Lorentzian rigidity is a big problem, and don't get the wrong impression that I solve it in the greater generality. No, I'm still trying to understand what it really even means. We'll see in a moment. So I'll start with the remaining case, because this is a good starting point. So in the remaining case, we have a compact manifold with boundary and metric inside. And for the purpose of this talk, let's say that the manifold is fixed, the metric is not. You want to reconstruct the metric. And you shoot from point on the boundary, you choose a point, you choose a unit direction, you shoot, and then you measure the outgoing point, the ongoing direction, which is 2 units, of course. And we call that scattering relation. And you may want to define the length relation, which is the following. So add to that the travel time. So because this relation doesn't really measure the time of travel, roughly speaking, which will be the length of the geodesic, which could be infinity in principle, let's say it's finite. So L, the small L, is actually the time it takes to get there, which is the length of the geodesic. So if you take this pair, this is called length relation. So in my opinion, those 2 terms should be reversed, because real lenses, you don't really have a sense of time. But anyway, this is how it's called. A better way to think about this is actually to project the unit vectors to the tangent space here and there. So then those projections of length 1 or less, they belong to the unit ball at any point. And you think about the scattering relation as a map from the cotangent ball bundle to itself. And if you know that, you can always reconstruct the unit vector which has this projection, which points inside. So this is a better formulation, because with that formulation, if you take diffeomorphism, which doesn't change the boundary point-wise, S is actually preserved. If you don't do that, if you keep the original V, well, it's not quite preserved. So this is actually the proper formulation in a way. Okay, so we call MG scattering rigid if the scattering relation determines MG uniquely up to an isometry, which fixes the boundary point-wise, and clearly isometry will not really change that data. In other words, okay, if that holds. So what is length rigidity? Well, it's similar, but you use additional piece of information. You use L as well as part of your data, and you want to do the same thing. Okay, again, that was the remaining case. So what is the boundary rigidity problem? So you fix a pair of boundary points and you measure the length of the, well, you measure the distance between them, but if you assume so-called simplicity, in other words, each pair is connected by unique minimizing geodesic, that will be the length of the geodesic which connects them. So in other words, you measure a scalar function instead of vector map as before. And locally, this function again maps R2n minus 2 to R, because it takes scalar values. And the scattering relation maps same number of variables to, again, vector space as well. So it has many more variables in the image. But in fact, S has a structure. This is a symplectic map. And it is the canonical map of the hyperbolic Dirichlet number map, which is associated with G, if you start thinking about wave equations. And clearly, that will be overdetermined because of this special structure. And if you assume that X and Y are not conjugate along the unique geodesic, that you assume that is unique, that connects them, then we can define our rho locally, the distance, if you just take all geodesic which are only close to this one, ignore the rest. And then this rho is a generating function of S. So you can express S in this way. Of course, there's something hidden here, is that you can actually solve for this vector, let's call that V prime, as I did before, but this follows from this non-conjugacy assumption. Okay, so again, this is probably not too much surprising. So this is a symplectic map, which doesn't really mean that it has a generating function exactly of this type, but under this condition it does. And then rho, which is again just a simple single scalar function, determines all those functions S and L. In other words, this is a little bit too much information. It's enough to have rho in this case. Okay, so this boundary distance function has another advantage. If you try to linearize near a metric, we get this nice looking X-ray transform of two tensor fields. And F is the perturbation of the metric, and actually this is the typo here, this should be G. So delta means perturbation, it should be G. Now you can linearize the scattering relation instead. Yeah, okay, that works. And we get an uglier X-ray transform that involves the gradient of F and some weights, which is some Jacobi fields, and it is vector valued on the top of that. So you can analyze it if you really want to. And actually, we did that with Günther and Anders in one of our papers, but that's not fun. That leads to a lot of additional complications, which you really want to avoid if you can. You prefer to work with this, which is more simple. But you can say, well, we have to assume these non-conjugacy assumptions, which for, okay, so I can see another typo here, which is kind of simplicity, local simplicity assumption. That's not a big deal, because if you know the scattering relation, you can determine the jet of the metric at the boundary. Then you can extend G smoothly in a known way. And then you can just push Y a little bit away from the boundary. And then X and Y will not be conjugate. And then all that will work. So I understand this is a little bit vague. More about this will come later, but it's not really a big problem that they conjugate to themselves for something like this to work. And actually, we use that trick with Günther in some of our old papers. Okay, so there are a lot of works on Riemannian rates of scattering or boundary rigidity, and you can see some names here, and this is very incomplete list. It's a huge topic, and I don't want to say more about that. It is known that in the neighborhood of an open set of simple metrics, and simple means strictly convex boundary, no conjugate points. In the neighborhood of such a set, we know that we have boundary rigidity, which implies also length scattering rigidity. This neighborhood includes simple real analytic metrics. We use analytic macroanalysis for that. And we have local uniqueness up to the gauge and stability. Now, if we now have this foliation condition, which means that we have a strictly convex boundary, but you can keep going inside with the convex foliation. Then we also have boundary rigidity, which is a recent, well, maybe 2-3 years old result with Günther, Anders, and myself. And in particular, if you have non-positive curvature and simple connectedness, non-negative curvature, those are sufficient conditions, plus strictly convex boundary. We even have local uniqueness. Local here means near a point. Before it meant near a metric. Okay, so the linear problem has been studied a lot as well, and there are many papers by more or less the same authors. I want to mention also Francois here as well, who did a lot of work on the X-ray transform, geodesic X-ray transform. And under some conditions, we have injectivity and stability. Partial data problems have been studied and understood. And actually, this foliation condition first appears with paper by Günther and Anders. And you can call that, if you want, support theorem in 3 dimensions and higher. It's a partial data problem. Contribution of conjugate points also can be studied. Okay, so that was about the Riemannian case, because you really want to understand well the Riemannian case before we get further. Now the Lorentzian case. So mg is Lorentzian, and now I want to localize it. I take some points here, x and y, and take some small neighborhoods of the boundary. In this picture, the boundary is time-like on both sides, but it could be time-like on one side and space-like on the other side. That's not a problem. And it take a point, it take a null vector or light-like vector. In other words, it has length 0 in the metric. And then it shoot from this direction. You have some orientation. So in other words, there's a notion of future and past. And then it hits the boundary again. And this is the exit point and the exit vector, which is still light-like, of course. And I restrict everything to those two neighborhoods because for my considerations, the rest of the boundary doesn't really matter. And I'm not proving any rigidity at the moment. I just want to understand that map in the first place. And you can have two space-like surfaces and do something similar. And actually, this is what we did with in the joint paper with Günther, Matti, and Lowry when we study so-called cosmic strings. Okay, so this is a scattering relation in that case. And as before, it's better to project orthogonally to the tangent space on the boundary instead of studying V, you study V prime and something there. Okay, there's a small problem here, which is actually not so small, it's interesting. There's no natural parameterization of null geodesics. There's no unit speed here. If you multiply this vector by any constant, it's still null vector. And it's not worse or better than the original one. And actually can change that constant, that parameter, if you move from point to point, direction to direction. So there's no natural parameterization of those null geodesics. Okay, so we'll get to this later. Okay, so that's not a big deal. We just think about S as a homogeneous of order 1 in its second argument, which is consistent. We think about this being canonical relation or something. So it is useful to lift S to the cotangent bundle, and I call this map S sharp, right? We proved that with Young that this is, I mentioned this before, is a canonical relation, again, of the TM map. So it is symplectic. In other words, when I mention symplectic and so on, I always actually think about that, not about S. And there's a trivial way to pass from one to the other, of course. Okay, so the first question I want to understand is there an analog of the boundary distance function in the Lorentzian case? And now I have to set up some conditions. So when I say analog, you say, okay, but of course we have Lorentzian distance, so why don't we just take this? Now I want this R to have the properties as rho has, and let me list them. We want this function and the scattering relation to determine each other. We want R to be the generating function of S. In other words, instead of studying this transform, which is vector variant, we just want to study scalar function. You want the linearization of R to be this Lorentzian X-ray transform of tensor fields. Why? Because, well, this is much, much simpler than linearizing S itself. And why we want to do that? Because this gives us some hope to solve the inverse problem by linearization. I'm not saying that we actually are close to doing that, but at least in some cases we could. And one problem is that L, this operator, misses time-like singularities, which moves faster than light. We'll say more about this later, but okay, this is what it is. So in other words, this is the first question I want to answer. It's more like philosophical question. So what is the natural analog, natural in that sense, right, of the boundary distance function? And this is the, you may say, okay, why don't you use the Lorentzian distance? But the Lorentzian distance kind of singularity is 0 on one side, and then it has some singularity when it changes from 0 to something else. It also depends on not just light-like geodesic. You have to know something about time-like geodesics too. There's also separation function, which is singular. I mean, they don't seem to answer the question. And now I can tell what answer I'm giving at least. So you see this non-conjugate assumption that was shown on some of the previous slides, but now this is the Lorentzian case. I'm assuming that we have 2 points which are not conjugate along a fixed light-like geodesic, right? So far, I'm assuming. Okay, so now I want to. One problem here is that if you just take 2 points, they may not be connected by light-like geodesic. In the remaining case, every 2 points, well, at least if you see something, the geometry is not too bad, are connected by some geodesic. Here they are, but I want to be light-like geodesic. And that may not happen, right? If you take 1 point, there's a light-like cone, which intersects the boundary, and that gives you some kind of submanifold. And if you're not on that submanifold, they're not connected with such a geodesic. Okay, so this set sigma I define consists of pairs that are connected by unit light-like geodesic locally. And then you just take a defining function of that set. So what is the defining function? What is 0 on that set, which is a smooth submanifold of codimension 1? It has no zero differential. And I just take this sign convention here, which is just convention, right? So it's not a big deal, this condition I, 2. So in other words, this will be my answer to the analog of the boundary distance function. Just take this set of points, again, of pairs, which are connected by light-like geodesic, and take any defining function of that. Of course, there are many defining functions, but they all differ by elliptic factor, and we can deal with that. So here's the first theorem. So we have all those assumptions. Non-conjugate assumption is the most important one. So again, sigma is a set of all those pairs, right, which are connected by light-like geodesic. It's a codimension 1 submanifold, and everything is local here. And then I take every defining function of it. And then if we take this set here on sigma, of course, this coincides locally with the graph of some reduced representation. What do I mean reduced one? I mean, this is homogeneous in its second argument. Anytime when you restrict those 2 variables to some transversal surface so that you reduce the freedom to rescale it, I call that reduced representation. Roughly speaking, if you can make them unit, okay, that will be reduced representation. And if we have 1 parameter family of metrics and you linearize this R, what we get is the transform that you really want to get, written in some fancy form here, times some elliptic factor, kappa. Right? So again, that was my goal, right? So I wanted linearization to lead to this transform that people study even before we know that it will be useful. Okay, so the non-uniqueness of the defining function is actually quite of natural because there's no unique parameterization of no geodesic in the first place. That leads in some sense to non-uniqueness of this defining function. And that explains, I'm going back now, to why we can have this elliptic factor here, which is basically arbitrary. Of course, eventually you want to see what happens if that is 0. If that is 0, this factor doesn't change anything. But again, this factor here, it is can be expected. Every other defining function is obtained by any fixed one by multiplying by such a factor, and that will bring that factor in that linearization. So here I have some very short explanation of that, but this is basically the idea. And since S is homogeneous in the second argument, it's enough to have it just for one of these factors. Okay, and this is what I mentioned before, right? So those 2 facts that there's no unique parameterization of null geodesics, and you have this elliptic factor, they somehow play together very well. Okay, so the graph of S sharp, remember this sharp means it is considered in the cotangent bundle instead of the tangent one. So this is actually the way it's written. So going back to the previous slide. Right? This is exactly the twisted conormal bundle of sigma. Sigma is that manifold of pairs. And again, going back, why twisted? Okay, because we have this negative sign here. And this already follows from a characterization of it as a canonical relation of some FAO. To be more precise, it follows because you can see there that under the non-conjugacy assumption, the Schwarz kernel is actually conormal to sigma. Right? Without this, it will be a little bit more complicated. But here we get it directly without thinking about full integral operators. Okay, as a corollary, we get that the scattering relation determines this defining function uniquely up to an elliptic factor, and each defining function determines S uniquely. In other words, you don't really need to study S, you need to study R from now, which is just a single function. And now this legitimizes the interest in L. In other words, we study L because we kind of guess that it may have something to do with the nonlinear problem. And in our paper with the strings and so on, actually, we proved that in some particular case. Well, now this shows that L is really linearization of something important related to the nonlinear problem. It's not just analog or something. And the proof is constructive. We construct one such function. Every other one is, of course, trivial to construct if you know one of them, using the concept of energy. So if you have a smooth curve, then the energy functional of that smooth curve is given right here, right? And each geodesic doesn't have to be light-like. Connected to endpoints is a critical point of this functional, but unlike the remaining case, I'm not claiming that this is a minimizer or maximizer or anything like this. I mean, roughly speaking, this is something like how do you call it? Not inflection point, but a point where you can have in one direction minimum, the other or maximum. This is very roughly speaking. So I'm not making any claims about minimizing or maximizing anything. But it is a critical point. And the proof is very simple because the proof is based on some differentiation, which doesn't really care if you have Riemannian Lorentzian metric. You just use calculus conormal derivatives, and it is well known. Okay, so now take a family of metrics, Lorentzian metrics, and take the geodesic that connect X and Y in that family of metrics, and then you don't have to be like, and you just differentiate with respect to parameter. If you differentiate, I mean, the metric appears in several places, right? C another geodesic that depend on the metric, it appears here as well. If you differentiate everything except that, you get 0 because of the minimizing property of the function. The only non-trivial term you're going to get if you differentiate that with respect to the parameter. And again, this is well known in the remaining case. So this is the linearization. And this is exactly what we want to show, that the linearization is some factor, elliptic factor, times the light-late transform. And then you can just set, okay, R, the defining function, is going to be the energy of the geodesic that connects X and Y. So this is a way to construct it. And then you can multiply by any elliptic factor if you want. And if you go back to the remaining case, just to do a sanity check, I mean, we have all this new concept, but it doesn't really agree with what we had before. So if you have remaining metric and want to think about this as Lorentzian metric, you add minus dt squared, and you have complete separation of variables here, of course. Then this will be good choice of defining function. So rho is the remaining distance, right? Only related to that. and t and s are just two moments of time, arbitrary on the boundary. And this is 0 if and only if the distance between those 2 points is exactly equal to the time difference, which means that they're connected by unique light-like geodesic. We can also take this function, and it's a very simple exercise to see that if you compare this and that, one of them is elliptic factor times the other, right? Just you have some times difference, right? Okay, so this is another choice of defining function. But what if you use the energy, as I did in the previous slide? If you use the energy, do all the computations, well, you get this one, but divided by s minus t. Well, it's another possible choice of such defining function, right? Because you have the freedom to put any elliptic factor here. So in other words, if you go back to the remaining case, you really get what we had before, in a way, right? Okay, so again, this answers the first question that I want to answer is, well, is there an analog of the boundary distance function which make our life easier eventually if you can do the next step, which would be linearization and so on. Okay, now I want to say a few more things about gauge invariance, which is well known, but I really need to recall all those facts because that will be introduction to the second part of my talk. Now, going back to Lorentzian case, general Lorentzian case, first you have invariance under diffeomorphisms under which fix the boundary point-wise. U and V are just piece of the boundary, right? Well, you know that. If you linearize near that, we get that this linear operator, the X-ray transform, vanishes on so-called potential fields. And those potential fields are just symmetrized covariant derivatives of all vector fields which vanish on the boundary. Again, this is the same in the remaining case. It works in the same way here. That's nothing new, nothing surprising. But we have additional invariance under conformal changes. Again, this is well known. If you put a conformal factor here, why I want to be 0, positive? Well, it could be negative, but this would change my orientation, what is future, what is past. So let's keep it positive. The factor C just changes the parameterization of light-like geodesics. It leaves them the same as curves. It just changes the parameterization in a nonlinear way. But the scattering relation is preserved. After all, it's homogeneous, the second variable, so I don't really care about it. So if we linearize this, we get that the light ray transform of CG is 0, but that's kind of obvious by itself because integrating CG point and pointwise, G of gamma dot is 0 because this is light-like geodesic, and this is just a factor which multiplies 0, so you still get 0. So this is absolutely trivial on the linear level, and it's not so hard to prove in the nonlinear level too. So those are the two known, at least obvious, invariance groups of transformations. And then you can formulate what you think scattering rigidity should be. Scattering relations equal means that first you can apply such a diffeomorphism and you can multiply by conformal factor. And other than that, there's no other transformation that will preserve the scattering relations. And on linear level, it should mean that LF equals 0, F equals symmetric field, well, potential field, right? And what is new here is scalar function times the metric itself. And again, those are conjectures, right? I'm not saying that those are theorems. This is how I define it. Again, all those formulations are not new. Okay, so what do you know about invertibility of L? Well, invertibility under this class that I mentioned, it has a micro-local blind spot, roughly speaking, right? You cannot see time-like singularities, which is very easy to see. And stable inversion is not possible unless we assume some additional structure. And in the paper by Anders and Wang, they actually assume that you invert it on functions that solve wave equation. They have additional structure, and then the inversion is stable, but otherwise it's not. So you have injectivity of functions supported in the cylinder, for example, and the proof is using partial analyticity of the Fourier transform with respect to x, because we assume compactness of supporting x. Otherwise, it's not true. So this can be extended to analytic metrics in certain correlation condition. It can be extended to one form for Minkowski case. Rabin-Har, Batarka, this is one of my students. And then there's a recent paper, well, I don't know how recent, maybe 5-6 years old, but anyway, a paper by Laszlo, Oksana, Günther, and myself, micro analysis of the Lorentzian metric, Lorentzian case, if L acts on functions, and also on two tensors for metrics of expanding universe, which is the so-called strings paper. And the paper that I just mentioned before by Wang and Varshy. And another paper, Wang micro analysis, it says something about flight-like singularities, which is kind of borderline case. And then there's a paper by Lowry, Mavrinta, and Faiz Mohammadi. Okay, so he worked with him. So this is a result for stationary metrics. And I'm going to say more about stationary metrics in the rest of my talk. In particular, they proved that there is injectivity up to the gauge for two tensors of compact support. And that's not trivial at all. It's quite tricky, actually. Okay, now second part of my talk is rigidity of stationary metrics. As I said before, there's a little hope that you can do something more general case, because after all, there's this blind spot, how I call it, microlocally at least. But in some cases, we have more hope. And one of those cases is stationary metrics. Well, they're just Lorentzian metrics where the coefficients don't depend on time, roughly speaking, in some coordinate system. And you can write them this way. I put tildes here because in a moment I'm going to write in a slightly different form. So there is no t dependence on the coefficients. And you can complete the square. So it's very convenient actually here. Write it in this form. And you can determine this omega and h in terms of the original ones in a very easy way. So there are three objects here: lambda, this conformal factor, the one form omega, and the metric h. We postulate that you want this to be Riemannian. And then you have the right signature here, if you do that. Okay, this form can be derived from some global assumption of global hyperbolicity and the existence of complete killing vector fields, which eventually turns out to be DDT. I don't want to go there, but you can formulate it in a more abstract way. For me, this is just given locally in this form, but then that form actually makes sense invariantly. So a natural manifold will be a cylinder because the matrix somehow has separation variables. So we want to assume that the manifold is of product form as well. And now we know that certain transformations preserve the scattering relation, but we want to stay in that class. So now the question is, which diffeomorphism will preserve that class? And you can easily see that diffeomorphism in the x variable only, which fix the boundary, will preserve the scattering relation, which is kind of trivial, easy to see. But of course, now we're in Lorentzian setting, right? So you can expect diffeomorphism which somehow change the time variable as well. And another group of transformation is the following. You do time shifts, but you do them depending on the position. So the x-dependent time shifts. And they fix the boundary if you assume that phi is vanishes on the boundary, which I assume. And now I'm going to show a picture on the next slide. I'm going to return to this one. So the first group of transformation just shift things horizontally, roughly speaking. And the second one shift them vertically. And of course, they preserve the boundary, but the shift, those are time shifts which depend on the position. Okay, so that's, and you can see with a little bit more effort that you cannot really find easily, at least, transformations which preserve the boundary, which preserve the structure as well, different from those two. I'm not proving that because eventually I'm going to prove it in different way. Now we have two metrics which are stationary that depends on those three parameters, right? We call them gauge equivalent if they exist a diffeomorphism and a function that satisfies all this that you see here. And then you see that if you do this, actually, this kind of transformation, this replaces the form, the one form by form plus differential of another exact form. Not another, but by adding an exact form. Okay. So this is our understanding of what gauge equivalent should be. Now we want to show that scattering relation determines the metric up to gauge equivalent class. You see, there's nothing about lambda here. For a good reason, because lambda is a conformal factor, which actually doesn't change the scattering relation at all, right? That's why, going back, that's why I'm putting this in this form, because I can simply ignore this, because it doesn't change S. If you leave it here, well, you have to divide by lambda, but you have to divide everywhere. Okay, so what are prior results about that? So this is the paper that I mentioned earlier. It's about the linear problem, actually. They project the dynamical system onto the base N and get certain dynamical system there, which depends on X variables only. And then derive results about the linear problem depending on assumptions about the behavior of that system. Well, that system doesn't look very nice in that paper, but actually, I'm going to show in a moment that you can recognize it easy as one of the systems can be studied before. And also there's a paper by Günther, Young, and Zhu that they use time separation functions, so it's somewhat different data, which takes into account time-like geodesic. And there are more restrictive assumptions on the one form, but they treat the nonlinear problem, right? Not about L, but about the scattering relation. And they prove that you can have rigidity. Okay, so recall this is the metric, the way the form they put it. Take lambda to be 1, and you project M on the base. So I have to warn here that this is not orthogonal projection. It is just identify all straight lines with points. So here's some picture, right? So you have some light like geodesic, and then you just project it onto the base. And basically, you want to reduce the whole problem to a problem onto that base. What is base? Base is M by definition. Now it turns out that this projection to the base is a magnetic system. So if you think about this, what else can it be? And I have to say here that this is first I heard that argument as a way to prove theorems from Maciek. So he used that as a joke when he gave this talk on semi-classical analysis at Berkeley, and I like these jokes. I reuse it. So you have a Riemannian metric in one form, and the actual proof that this is a magnetic system was provided in this paper here in 2007. I didn't know about this paper until recently. And it's very important here that I remove that lambda here, right? Because it doesn't matter for our problem. If you keep lambda, which multiplies the whole thing, it's actually more complicated to magnetic. You have magnetic and electric field. It gets more unpleasant. But now it's just magnetic one. And now rigidity for magnetic system was studied by in paper by Rybakov, Gabriel, Günther, and myself years ago, and we proved a lot of results. And now that my point is that every result we prove there translates immediately into a result for stationary matrix. Okay, so what is a magnetic system? So magnetic system, now I'm in Rn, right? There's no time anymore. Right? So this is just, roughly speaking, some generalization of remaining case. So H is a remaining metric. And you have a close to form omega, and at least locally you can think that it's the derivative of some form omega. And then we can define this linear operator on the tangent bundle, which is basically d omega with some index raised, and it is antisymmetric. And then the dynamic is given by that. This is covariant derivative, and if you put 0 here, it doesn't do geodesic, right? And what this does is adds additional term in the geodesic equation. So this is a force which is always perpendicular to gamma dot. And you think about this as action of magnetic field, which tries to change the velocity always perpendicular to it. And if H is Euclidean and Y is constant, it actually gets space spirals. Very simple description. And the speed is preserved along the flow. It's very easy to prove. And you just fix it to be 1. If you fix it to be something else, you get different curves. So you have to fix the energy level. And then you can also have the notion of travel time, of course. And the natural boundary data is not the travel time. It is the action, so-called action. So this is a travel time. We expect it to be a travel time, but then you have to subtract that. This is the geodesic connected boundary point. And this is the object which replaces the boundary distance function in that paper. So I'm still talking about this paper that was written more than 10 years ago. And magnetic system gauge equivalent if metric is isometric to another one, and if the one form here is also obtained by this isometry plus adding of exact form, and phi is 0 on the boundary. So this is the natural gauge invariance for magnetic systems. And again, this is a very long paper, like more than 50 pages. I'm trying to correct some of the results here. So if you linearize A, you see not the time of travel, you linearize the action, you get this transform here. It's a sum of two transforms that have been starting load, but now it's a sum of them. Okay, that still can be analyzed. A determines the magnetic scattering relation and vice versa. Again, A is a scalar function, right? So it's much simpler object than that which is vector velocity. And S injectivity means, talk about the linear problem now. F is a potential field, but again, this is the form that I call beta now, before we call it omega, then I don't know too much. Well, I should have put here if the linear transform is 0, which is missing here, I should put it here, then F is potential, beta is not just that, this additional factor, right? This is the meaning of S injectivity. Then in those cases, we have S injectivity, which means linear operator is injective up to the natural kernel. In those cases that I have here, and since I have only 5 minutes left, I'm just going to display them without even reading them. Okay, because on the next slide, actually going to see some of them repeated. Okay, so what is gauge equivalence now about the nonlinear problem, right? Before it was about the linear. And some of the results in that paper is a two-dimensional simple magnetic system boundary rigid in other conditions. And that follows a result by Günther and Pestov. And there's no linearization here. I mean, this is one of those papers that basically came from nowhere. And the method is very original. So you can reconstruct conformal factor. A real analytic simple magnetic system gauge equivalent. This uses microwave analysis, analytic microwave analysis. And we have generic local rigidity near simple magnetic system with S-injective linearizations. In other words, you can solve it by linearization, and that gives you generic results. And now back to stationary metrics. Okay, you have 3-4 minutes, right? So if you write the light-type geodetic for stationary metrics in this way, then you prove that this is the geodetic equation, which is kind of almost decoupled. So those are magnetic geodetic. K is just a constant, long-Kish geodetic that you can choose. You can actually change by changing parameterization here. And once you solve this, you solve the first one, and that tells you that T is an action variable, it's not really time variable. And then the whole point here is that if you know the scattering relation for the Lorentzian case for stationary metrics, you can actually reduce it to the magnetic case, and then derive all results from there. And let me just skip quickly because I have only 2-3 minutes left. So this is the main result about stationary case. So again, G depends on those 3 parameters, and lambda actually doesn't really change anything. So you assume that they're simple, and simplicity means if you project it on the basis simple, right, in stationary. Then the same scattering relation means they're gauge equivalent if and only if you can say something about same thing about the magnetic system. And there are lots of results with them, as I mentioned. And here's some corollaries. 1 + 2 dimensions for simple stationary manifolds. We have rigidity. In a given conformal class, yeah, we have that too. Right? All that just follows directly from the result in magnetic case. And the final one, the generic result, which is the hardest one to get in some cases, well, maybe, depends. So there exists an open and dense set. This Fanny G or CK is actually a subset of CK, which is the functions of tensors with finite smoothness, such that if you stay near that set, then you have local rigidity near any pair in that set. And you may say, okay, but why don't we have it for all of them, something even better than that? Well, stationary metrics involve the remaining case as well. So it's more general than the remaining case. And we have enough troubles with the remaining case, and we have great results there, but not really complete answer to this. So you cannot expect a complete answer here either. Okay, so I'm done. Right on time.
Thank you very much. Thank you very much, Plamen, for the very, very nice talk. Are there any questions or comments, please? Please feel free to unmute yourself. Are there any questions or comments?
Hi, Plamen.
Hi, Jeanette.
Yes, Jeanette. Okay. Very interesting talk. I enjoyed. So, about this problem, if we are looking at this problem in the frequency domain, I suppose time will be disappearing, and a lot of things can be just look at in the Riemannian metric sense. Because this will work at least for linear wave equation, time space wave equation. Now here probably it's nonlinear, so you cannot go to the frequency domain.
Well, first, in order to do this, you really have to have some structure like stationary metrics. Otherwise, there's not really time, right? Let's talk about stationary metrics, right? Mm-hmm. There's a kind of time fixed. So we're not studying wave equation, right? We're studying problem in integral geometry. if you think about wave equations, you can take Fourier transform, you can make it stationary. But in the paper that I mentioned before, let's see, Laurie is involved there, but I want to display all the authors. Okay, this one here. They actually take Fourier transform. They started doing a problem, but they take Fourier transform in time. And it's a very clever argument. And they get injectivity about this transform acting on tensor fields. In Minkowski case, not just Minkowski, even more general cases. But doing what you said, just take Fourier transform in time, think about harmonic analysis that was in the time variable. But then F is completely supported in space and time. So there's an elasticity in time as well. And they recover the Taylor expansion of F hat with respect to tau. Tau is the dual of the time variable 0. So some kind of that analysis done, but you might be thinking about actually wave phenomena. So we're still not talking about wave equation. Not sure that's the question.
Yeah, so because for linear wave equation, if the coefficient sound speed stationary, then these you see if you have ansatz like Mark log ansatz in the frequency domain, you naturally will have ansatz in the time space domain. So that's my intuition. That's why I'm asking the question. Yeah.
No, I mean, it's easy to do geometric optics. Well, it's easy or not, I don't know, but it's routine in a way. You can do geometric optics, but again, there's no really wave equation here. Eventually, that data, this is motivated by application to wave equations indeed, but right now, we stay away from wave equations.
Okay. So another question is that how computable about in terms of your theoretical results?
Okay, I mean, you have one more interesting variable, which is time. So you want to study at least the 2 + 1 dimensional case. So you tell me. So you have basically 3 dimensions, but it is a restricted transform. So, but still there are more dimensions. That is, it's not like doing tomography in 2 dimensions. I think that it might be, there's at least one more variable. I was thinking about actually doing something just to invert even the Minkowski case on functions and to see what happens near the light-like singularities and so on. Again, you're an American analyst, not me, but I think you need at least one more variable in the calculations.
Okay. Yeah.
Compared to the dimensional case, the dimensional one.
Yeah. Thanks. Yeah. Very good.
Thank you very much. Are there any other questions or comments, please? Any other questions or comments, please? If not, thank you very much, Plamen, for the very, very nice talk. Thank you very much, everyone, for coming. Thank you very much.